Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, it's good to have Mohammad Hajiagai visiting us from University of Maryland. He's here till tomorrow and he'll be speaking about some graph miner algorithms.
Yeah, thanks a lot for the introduction and for inviting me. Okay, so let's start with the talk. Of course, I mean, you will see the title of the talk and my name. Okay, so before going through that, I want to give just some introduction about the whole thing that we want to do. So here, what is the separator technique for getting PTASs, or actually not just PTASs, getting approximation algorithm? Usually you are considering the graph, you find a small separator for this graph, and then you cut that thing. Then again, you are finding a small separator in each of these graphs, you cut it, until all pieces are small. And this is essentially the idea of lots of algorithms, including the planar graph, PTASs, Lipton-Tarjan, and more general problem that we could just do it for H-free graphs, and actually also this work of Layton-Rao or Arora-Rao-Wazirani. All of them are essentially doing that. More precisely, so here all of this separator decomposition, they are finding small separators, and they continue such that we get small pieces. Now, what do we want to do here? We want to do simplifying decomposition. Essentially the same idea, but maybe we can do it more than that. So here we want to have these two properties. We might have a large interactions between these guys, so these are not small separators. And the graphs that we obtain, also these are not small graphs, it might be very big graphs. The only catch is that they should be algorithmically simple. That's the thing that we call it simplified, or simplifying decomposition. So this can be arbitrarily large, this can be arbitrarily large, but algorithmically simple. That's essentially the whole goal, and the whole goal of this talk is that we can do this for what kind of graphs. I mentioned some here, and then that would be, I think, the whole agenda. Can you do it for more graphs, get the same thing or not? Like, that's essentially the whole talk. You saw the abstract of the talk. Now let's see a bit more details, and I will again go some basic definitions very fast. I will go there, then I will say the main theorem and the applications of that. If we have time, I will go through the proof of them, which is a bit involved, I will say. But I think that should be enough for the main thing that you want to get from this talk and why these are interesting. So the minors, we say that a graph G is a. Let me just do this one. So hopefully nothing will break down. If I just change this one to here. Now I can go here. Okay, good. Now, we say that a graph H is a minor of a graph G if we can obtain H from G by these two operations. At each step, either you delete an edge or you contract an edge. And say if the graph is connected, in the minor, we have this definition that you can delete the vertices also. But if the graph is connected, you don't need to actually delete a vertex. You can always get the minor by these two operations. Because anyone that you want to delete, you will just contract it, and that's it. And we don't keep the, OK, and in the contraction, we don't keep the loops or multiple edges here. That will be destroyed, essentially. We will just get one edge. And this is the example. K33 is a minor of this graph. I mean, it's up to you to find it why this is the case, but that's a nice thing set. This graph is essentially, and it is called the map graphs of the US. But anyhow, these are all coming from this graph miners of Robertson Simmer from 1983. We don't know what is the end. They are publishing, I think, some. So I think 23 of them have been published yet, but they still are maybe more to come. But the main things that essentially that's the 21, that was the main idea was to proving the Wagner's conjecture. That essentially, that's the Wagner's conjecture. For every finite set of finite graphs, one of its members is isomorphic to a minor of the other one. That was the whole idea, but lots of things came out of this graph minor. And in a sense, I mean, also this is some kind of more algorithmically thinking of graph minors, this one that I'm presenting it here. Okay. Other thing that we need to know is that treewidth is the measure of similarity of a graph to a tree. That's enough for this talk. If you want to see the exact definition, treewidth of a graph is the smallest possible width of a tree decomposition. And what is a tree decomposition? You have a graph. For each vertex of the graph, you try to smear this vertex into the, somehow paint it into this tree. And such that any two vertices that they have an edge, then their corresponding tree should share at least one vertex, and then, or overlap on one vertex, and the maximum overlap would be the -1 would be the width of that. But that's the definition. You don't need to know. I mean, such a definition. I mean, I will just.
There's a one-to-one correspondence between the trees and the nodes.
Yeah, exactly. Oh. So you mean no, between what and what?
The nodes of the graph and the tree?
No. This is arbitrary tree essentially. You can bound some. But I mean, for each essentially for each node of the graph, we have a subtree here that we smeared essentially. And we know the treewidths 1 are trees, treewidths 2 are third parallel graph, treewidths n-1 are cliques. So that's a good way of these are like how far. This is a measure of similarity to graph. And we usually consider bounded treewidths. And the only thing that you need to know about the bounded treewidth graph is that we can solve the problems easily in polynomial time for bounded treewidth graphs. That's the only thing that you need to know and nothing more. So if it is a bounded treewidth like trees, we can solve all problems. We can solve them essentially almost all problems for bounded treewidth graph as well. Okay. Here we consider 3 algorithmic goals. We want to essentially have algorithms which are correct, fast. By fast means polynomial. Correct means optimal solution. And we want to get hard problems, essentially NP-hard problems. Unfortunately, so far we cannot get all of them at the same time. So we need to get any 2 of them. Namely, if you get rid of the hard problem, cross out the hard problem, then it would be undergrad courses essentially. So we don't want to do that. So we will we cross out the other things, the correct things. We don't get the optimal solution. Okay, we cannot just say that we don't get the optimal solution, but still we want to be near optimal. That's the thing that the approximation algorithm is coming, or PTASs, which are 1 plus epsilon for arbitrarily small epsilon. That would be somehow ideal case essentially, PTASs. Not in terms of their running time maybe at least, but in terms of approximation. Still they are polynomial also. The other thing that you can cross out is the fastness. So if you don't want to have the fast algorithm, okay, again, we cannot tolerate to do not have any conditions on that. But we don't want algorithm like n to the k. So usually if you have some algorithm like a problem, you can like say vertex cover of size k, for example, or dominating set of size k. You can just, if you say this is the k vertices, you can just guess these k vertices and then try all things. Then the running time would be n to the k or n to the k plus 1. That's not good. We want to get it f of k times n. That's the thing that we call it fixed parameter algorithms. I mean, maybe 2 to the k, but it's still f of k times n to some constant which is independent of. So is it clear so far? Any question? Let me know. Okay. Now let's go to the algorithm that we have. So this is the simplifying graph decomposition. The first thing that I mentioned, and I will mention some applications of that. Actually, they are quite nice. Lots of these applications that I mentioned, these are open problems that the people worked a lot on that. And by this simplifying decomposition, it is almost trivial essentially to solve. Okay. Now, what is that? The first one is this one. Any H minor free graphs, the vertices or edges, actually both are important, can be partitioned into k pieces such that deleting any one piece results in a bounded treewidth graph. For arbitrary k, you can't do that. So you give me the k, I will do these things. And this gives essentially polynomial time algorithm for several problems, and even PTASes when we put k equal to 1 over epsilon. And this treewidth actually is bounded by k. So it's linear in k actually. So that's essentially the theorem. You will see, so I mean, you can see here, for example, you will delete this one, then the graph, each of them, if you delete, you partition this thing, each of them, edge set or vertex set. If you delete, then you get a bounded treewidth graph.
So k outer planars are also bounded treewidth?
Yeah, outer planars.
K outer planar.
K outer planars.
So it's very similar to it's in similar spirit.
Of the Baker things, yeah. But I mean, that's essentially, I mean, the one that now it is like very abstract things. You don't, and actually, the interesting thing, that works, for example, there is something that works even for more than H-minor free graphs. It is called odd H-minor free graphs. This is a class, again, more general than, that's the largest one that we can get it. That we cannot get it for arbitrary k, we cannot get it, but for 2, we can get it. So again, for some, maybe for some graph, you can get it for constant, you cannot get it for arbitrary k, but that's still good for us. You can solve the problem. Specifically, I mean, these are like, let's go with the big problem, like chromatic number. The problem is inapproximable n to the 1 minus epsilon until this is a very hard problem. But I want to solve it very easily on this graph, get a 2 approximation, it's like amazing. Even for 3 coloring, we don't have, we have only polynomial time guarantees. So in terms of approximation, it's quite weak. So, but this can, I mean, solve the problem essentially in a very good way. So we have this graph, as I mentioned, we have this generalization, that theorem that I mentioned, for the case of k equal to, that can be generalizable for odd H-minor free graphs. So consider like essentially odd H-minor free graphs or H-minor free graphs. And then just use that theorem. We are using that theorem for the vertex set. So what was that theorem? So that you can decompose the graph, the vertex set, you can partition it into 2 sets, such that any of this graph has bounded treewidths. Now what do you do? These have trees, say, or here it is a special case, it is trees. But for each of them, essentially, we can, these are 2 trees, we can find the best coloring for them. Because they are bounded treewidth graph, we can, I mean, dynamic programming can easily solve them. Then you will just solve them. And then what do? You will essentially say, here you are, for this one, you are using the color 1 to k. This one, you are using it 1 to k prime. Then you will use the color 1 to k for the first one, and then k plus 1 to k plus k prime for the second one. And this is a simple 2 approximation for the problem. Because optimum should do each of them, and each of them is at least optimum. So this is a...
Is there a way, is there any information about the edges between the 2?
I mean, can be arbitrary. Here the edges, I mean, you may, use something more. I mean, maybe that's, again, if you want to use the more practical things, maybe you can just do this one, get this one, and then try to do some kinds of like local search. See whether you can remove one of these colors and still use the colors. Right. Yeah, if you want to use the edges in between, also if you want to use it better. So you will just get that you have the guarantee of 2, still you are doing some local search, you may get a better solution.
Like for instance, like can we say theoretically that there would not be a complete graph between the 2? Like there would not be a bipartite.
Maybe, you can do that. So far, we don't have any guarantee. Okay. But, that's another thing that you may consider. Because the whole graph is H-minor free graphs. But, in general, maybe it is, because the whole thing that I want to say, actually, this is not the case. For H-minor free graphs, for odd H-minor free graphs, that can be a complete bipartite graph.
Like between the 2 partitions?
Yeah. So that's the interesting thing about the odd H-minor free graphs. Because the complete graphs, these are something that you cannot have it for the H-minor free graphs, complete graph of large size, because that's the meaning of H-minor freeness. However, a bipartite complete graph, you can have it for odd H-minor free graphs. And that's the interesting thing, that this problem can be generalized even for that. And then you can get a 2 approximation. let's see. I mean, essentially, I mean, these are, as I mentioned, these are very, and this is especially nice because of this Hadwiger's conjecture. Because these people, I mean, like in math, if you heard, the whole idea is that if the graph is, I don't know, k h minor free graphs, then you can properly color the vertices with h minus 1 colors. So here I say, I mean, this is algorithmically thinking of that. I don't care, I mean, how many, like maybe, I mean, they couldn't even prove this Hadwiger's for, I don't know, for c times h, I don't think that there is any proof even for that one. But here I say, okay, there is no need to prove. I mean, anything that Hadwiger is the best, I can get it twice that. And that's like, in a sense, algorithmically, I mean, maybe even a stronger that things. Again, not exact things, but 2 times that. Even for some graph, it might be optimum is much less than h minus 1, but we catch that one also. So that's like the thing that you can compare this one. Okay. Then you will get back. Let's see, I mean, another thing, the independent set essentially. So here you can get a PTAS. So you want to find the independent set, you want to maximum number of vertices such that there is no edge between them. How do you do that? You can get a PTAS again in h minor free graphs. Now you get equal to k equal to 1 over epsilon. For each I, you just delete that one. The graph has bounded treewidth, find the maximum independent set, and you just take the max of them. And this is easy to see, essentially, the algorithm that you will try everything here. And it is important that, I mean, for one of these I, you know that opt has at most 1 over epsilon here, or 1 over k here. And if you exclude that one, the rest we solve it optimally, so we get it a PTAS here. Another interesting thing actually that comes out of this one, these are all actually, we are using here also the vertex version of that, because we decompose the vertex set. Another thing that you need to, for example, use the edge set is, I think both of them actually, you can do for the this unique game conjecture, you can do for h minor free graphs, you can solve it by this thing for h minor free graphs. And like another thing that's actually simpler than that is the max cut. So max cut for planar graphs, you can solve it optimally. However, we don't know even for bounded genus graph that you can solve it optimally. But this is the algorithm that solves it for h minor free graphs. Why? Again, consider the max cut. Now you just do it for the edge set of the max cut. So you know that one of them, like if you divide it into k sets, one of them has less than 1 over k of the things. And you know that the max cut is always a constant fraction of the optimum. So if you make this number of k's large enough, you know that essentially you don't, if you add all those guys essentially here, you don't change the optimum. So you solve for the rest of the graph, the max cut, maybe you will add that part also. You get essentially epsilon more. So again, this is like a very important problem if you can repeat that, but it like trivially comes from this theorem. Okay, so that's, I mean, there were some examples that I mentioned, and both vertex version and edge version are important things here. Now, what about, let's consider other problem. Actually, that's again, so this came out of the more computer science set of problems. For example, dominating set or edge dominating set, all of these problems. These are the problems that are closed under contractions. What's the meaning of that closed under contraction? It means that if you contract an edge, the size does not go up. But if you delete an edge, the size may go up. And like, for example, dominating set, if you consider one like the edge, if you contract one edge, the size does not go up because you can probably include both. If both of them are included, you will just include. It may go down. However, if you delete an edge, it may go up because this edge, this vertex could dominate this one. Now it cannot dominate it. You need to add one more. And this was essentially the whole idea that we consider like the closed under contraction only. We don't want to just delete. We want to somehow contract. And this is the theorem that actually, if you have a time, I will give some ideas of the proof. It's complicated, but this is actually very nice one. Again, can solve lots of problems. So any h minor free graph, its edges can be partitioned into k pieces such that contracting any one piece results in a bounded treewidth graph. Here, again, by contracting means contract this vertex and then remove any multiple edges or things.
But keep one copy of, like, keep it as a single vertex.
Yeah, I mean, when you contract, I mean, one edge, there's two vertices would be one vertex, and that edge, if they're loop or some multiple edges, you will just remove them. And keep one if there's multiple edges.
So contracting a piece would mean take a full subgraph and...
No, do it one by one. Consider each edge contracted.
Okay.
So that this edge would be one, now both endpoints would be one, and the neighbors of this would be the union of the neighbors of these guys. That's exactly the meaning of contraction. This actually, I mean, the first one, I mean, has been done by Phil Klein, but that thing that he mentioned was not that clean, essentially. So in his paper, I mean, that was the idea how, I mean, he was considering this one. I mean, he considered some kind of, instead of contract, he was considering compress. And it was not such a theorem. So he used it during some getting the PTASs. But we had it at the same time that 2005 for the minor, for the deletion version. So we could just figure it out. And then later in his journal version, he refers to the exact statement from us. That was essentially in this paper, that we mentioned it formally, these things. And this is a bit, as I mentioned, he does not prove such a theorem. He is getting it, the idea is there, but you need to get it for this one. But I mean, that you could generalize it for H-minor field graphs, apex minor field graphs, and finally, that we could get it for H-minor field graphs. That was in stock 2011. And that's essentially, so far, is the best thing that you can do for this graph. Again, let's see, I mean, some of this application. So essentially here, before we had a deletion, now we have a contraction. And the same thing again. Any K, you can do that.
So basically, it's like the deleted graph, except that you have one more vertex.
What do you mean one more vertex?
Like if you delete this part,
yeah,
this black nodes will go away, right? But if you contract them, there will be one single black node.
No, there is not one single one, because you may have this edge set here. One edge might be here, one edge might be here. You contract here, and one contracted here.
Okay.
So there is no one vertex. If there was one vertex, that was trivial, essentially. Yeah, okay. The whole idea is that, I mean, you have some edges. These edges might be one edge here, one edge here, one edge here. And these are indeed this case. So you may contract here, here, here. And there is no one vertex. If there was one vertex, yeah, that was trivial. But it might be...
connected piece. If it was a connected graph...
Yeah, then it would be one thing. But I mean, maybe here a connected graph, here a connected graph, and here a connected graph. And say this, you contract it, then you have a one-to-three graph. And that's actually quite non-trivial. I mean, this happens is at least was quite non-trivial for me. I will just give a few applications of that essentially. So this is the okay. So let me give, I mean, now a fixed parameter algorithm via this contraction decomposition. And we see how useful are these theorems, how powerful these things. So, but consider the k-cut problem. Remove fewest edges to make at least k connected components in a graph. Okay. Now I want to say that this problem is a fixed parameter tractable in H-minor free graph. Before saying that, like this paper, they had it, Kawarabayashi and Torop. They were working essentially for 2 years to get this result, specifically for this thing. But I mean, Ken was involved also in that work that we had it. But when we finally could prove that, then essentially they left it. They could use some of their ideas to generalize these things for the arbitrary graphs. For k-cut, we can get it. But, I mean, this result was the main thing that they were working for a long time to get it. And it was completely non-trivial. But see, it is trivial using this result. So, FPT, I want to say this problem can be solved in H-minor free graph, fixed parameter tractable. How? We know that the average degree of H-minor free graph is C of H times, essentially is constant as long as H is constant. So, I want to say that the optimum is at most C of H times K. Why? Consider the minimum degree vertex. Delete all its neighbors. How many you will pay at most? You will pay C of H. Consider, and now when this graph, when you delete it, the graph is, because it's a H-minor free graph, it remains H-minor free graph. So there is another vertex that now it has a CH. Cut that one. Cut until you have it K vertex. So at most it is C of H times K. Now, how can I do that? I will just use that theorem, contraction decomposition theorem, with C of H plus one layer. One more layer. And now if you have one more layer, you know that opt in one of these layers does not have any edge. Because the size of opt was ch times k, the opt that deletes the number of. So what is opt? Opt is some essential algorithm that deletes some of the edges. Now, you know that in one of these layers, so the number of layers is chk plus 1. In one of them does not delete anything. Now, if it does not delete it, it means that we can contract it in the cut problem. You just contract that one. Then you contract that layer, the graph has bounded treewidth. Now we can solve the problem exactly on that one. So the running time would be essentially, okay, this you can do it in polynomial time. Here, everything, the number of layers that you will get is ch of k plus 1. This problem on the bounded treewidth graph can be solved in 2 to the k times n. Here, essentially, it is linear in k, so I put it just k here. And just plus n to the order 1, essentially, for this contraction decomposition, which is independent of k. So you can get 2 to the k times n, you can get it for this problem.
But to know which one you want, you will have to contract each one of, you'll have to run this algorithm chk plus 1 times, contract each one of the.
Exactly. So you will do it, all of them you will do, have at most, chk plus, that would be, that running time is nothing comparing this one. Right. This is like k times that, which is still 2 to the k. So that's essentially the whole algorithm. That was, as I mentioned, that was important. Now let's see another problem. For the bisection. This is actually, Uri Feige had a paper for bisection for general graph. That was in stock, I think, 2006 maybe, or something like this. He couldn't solve the problem. Essentially, he's just considering for very special case. Even he considered balance cuts or something like this. But the main thing is essentially for bisection. So here, and he tried actually to get it a fixed parameter algorithm actually for them. Now I want to solve this problem. This is again another applications of this one. So what is the bisection? You want to divide the graph into 2 equal parts. Say the number of vertices are odd. Are even. So otherwise there is, I think you can generalize it for odd case, but say that's even. Okay. This is also another interesting thing that this problem is closed under not closed not only. Okay, so this is something you can ignore it for now. Okay, but this problem is easy on bounded treewidth graphs, even for vertex weighted graphs. What's the meaning of vertex weighted? It means that each vertex has some weight. Now you want to bisect this thing such that the weight of here and the weight of here are equal, if it is possible.
Equal parts means what? Like say, is equal number of vertices?
Equal number of vertices, yeah.
So you just need to divide the graph into equal number of vertices?
Vertices, yeah, exactly. So you want to get some kind of balanced cut. Okay. Somehow balance that you don't want to get it here. That's usually it is very important. This type of thing to balance such that you can recurse. Now you know the depth of this tree that you have it would be log n or something like this.
So what's the optimization problem here? Equal.
So you want to
into equal parts
such a minimum number of edges deleted.
Okay.
So you want a minimum number of edges deleted such that you can divide. Now I want to solve this problem again for H-minor free graphs. So use the contraction decomposition with opt plus 1 layers. Again, the bisection, because it's a cut problem, so this is essentially that's the main thing. So cut problems are very good for this type of algorithm because you can contract it, and in one layer opt does not have anything. Because does not have anything means that you can contract it. In the opt has been contracted, then you will solve it on bounded treewidth graph. Then you get to the opt these things algorithm. That's actually I mentioned. So Uri tried to get that was the main thing that was in Strike 2000 for general graphs, but I think that is a bit far from that. Okay, so that I mentioned it. Okay, now that's another problem. A PTAS for Traveling Salesman Problem. In a weighted H-minor free graph. That was a problem that the Grohe essentially mentioned. Can we solve this problem? Get a PTAS for this one. And several other problems like the PTAS for minimum size, edge connected sub-multigraph. That's the main thing that one edge, you can use it several times. That's the meaning of that. And fixed parameter algorithms for K-cut, that I mentioned it. So let me just page down. Okay. So that's another thing that we showed, that any minimization problem with the following property has a PTAS on H-minor free graphs. What is the properties that you need to have? Should be closed under contractions. That if you contract an edge, then the size should not go up, should go only down. It should be polynomial on graphs of bounded treewidths. Again, lots of problems trivially satisfy these two properties. The one that is a bit non-trivial is this one, that there is a spanner for this. What is the meaning of a spanner? Means that you can map this graph H, in graph G, to another graph G prime, which has these two properties. The weight of G prime is essentially almost in the same order of opt of G prime. Note that in this G, it is possible that G is a very big graph, but opt of G is very small. Here I want to say this is called also some kind of kernelization. Essentially, you want to do it, or I think the different fields, they call it different things essentially. Like in streaming, that would be some corresponding to some sketches essentially that you want to have it. So you want to get this big thing, you want to have some sketch, such that in this graph the opts, first opt should be remain almost the same here and there, and the whole graph, the weight of the graph should be like done to almost the same size of G prime. And that was known, for example, for traveling salesman for a long time. And the last one that you need to know, that if you obtain some solution for the contracted graph, you have contracted some edges and you got some solution. Now, if you decontract, so if you want to consider, if you find a solution for this graph, now you want to find a solution for the bigger graph, what you need to do, you need to only pay at most some constant times the weight of the edges that you have contracted. So you don't need more than, again, all of them you may pay it maybe a constant number of times that, but not more than that. That's again also satisfied for lots of problems. So let's see an example here. So that was the TSP problem. So PTAS for traveling salesman problem in weighted H-minor free graph. The problem that I mentioned, it was a decade open. So okay, for bounded treewidth graph, there exists such an algorithm that you can do that. And there are some spanners. These are very famous spanners for these things. Now, the only thing that you need to do that is from these things, if you see, we had everything here except these map things. I will just say the map things. That's essentially good. So when you have a solution, you found a solution for the contracted graph. Now you want to open the things and get a TSP for the traveling salesman for the original graph. So the issue is that when you contract this one, then you don't have that particular things essentially. You have some connection, but you don't have that TSP anymore. But essentially, the thing that I think this is some timer. It is there. So then, how do you do that when you uncontract these things? So essentially, for those edges that you will, when you decontract this thing, some vertices in these things have odd degree. You can add essentially an Euler tour of cost 2 times weight of this graph, plus this perfect matching that on the odd vertices that you will add it. And everything that here we will pay would be corresponding to the size of S. So not more than S. So you can pay constant times S. And then this graph becomes Eulerian. And then you can find the tour essentially there. And everything would be corresponding to S. So you can do that one, and then you can get a PTAS for that. Again, trivial. For example, this is something that Phil didn't had it explicitly in his things, but that actually you can't do it much. Okay, and the main bottleneck here for this problem that we have is that we need some spanner results for more. So this we don't have it for several problems. So the main thrust of work here is getting more spanners for more important problems. Okay. So here the rest of it, I want to just give you some ideas about the proof of these theorems. Again, I cannot give the whole ideas, but I want to say some of these ideas and how come they are, we can prove these things.
So
yeah.
for planar graphs, like these, what is the counterpart for these theorems? Like it was known this theorem. Like you said that was possibly there in Phil Klein's work.
Yeah, that was the thing. Somehow implicitly that was in the Phil Klein's work that you can get.
But it is not there in, let's say, GraphMinder works.
No, there is nowhere essentially. Yeah, that's a new thing essentially. That's like that. But again, so this one, essentially, so there were some Baker's technique that was there for a long time. But for example, that was not that explicit that here it exists. And it's not that general. For H-minor free graphs, you can get it. Okay, so here, let me just start with I think maybe I can just say some of the things on the boards before going through this one for bounded genus graphs. Okay, so let me just mention the ideas essentially for the board. So can we just maybe just use it here? I can use some of the things. I don't need that much of these things. Okay, so you can see it here, I think. Okay, so for planar graph, what do we do that essentially? If you want to get this thing, I want to just give you some ideas about planar graph and say how you can generalize it for. So for planar graphs, you have some. I will say for planar graph, actually consider. Always, that's essentially the other thing that we get it from this bidimensionality. Planar graph, in a sense, if you want to consider them, just consider the grid. Something like square root of n by square root of n grid. So this is square root of n by square root of n grid that you are doing it. Now, I want to say the deletion problem, and then we will see what will happen for the contraction. So for the deletion one, essentially we are doing that. For any k that you give me, I will get these partitions by this one. So I will consider, like for example, if you gave me k equal to 3, then I will consider the first layer are those that are 0 mod 3. So this one, 1, 2, and this is one again 0. The second one that I'm considering it is 1, 1 here. And this is the third one is 2 and 2. So these are the three partitions that I want to get it. And now, if I want to delete vertices or edges, that would be, if I want to delete vertices or edges, what do I do? Essentially, I'm just doing for the deletion. For example, if I want to delete this layer, I will just, for the edge version, I will delete all these edges. And here I'm deleting these edges all. Maybe I also delete this. So these are the edges that I delete to get the result. And now each of them has essentially bounded treewidths that you can get it. So, and in a sense, you can consider that we are doing some BFS from this vertex. If you consider some so connecting it to here, say, you are doing essentially BFS layers, I mod, like a I mod k for any I. You will just do that and you will delete this thing. If you want to delete vertices, then for example, you just deleted these vertices. Now, if you want to do the contraction, the version, that's a bit more subtle. But in this case, essentially, you will consider, if you want to do for contraction, what do? You will delete on the dual of this graph. And note that one of the things, we can first generalize it to bounded genus graph. Bounded genus graph, still they have the dual, but H-minor free graph, they don't have any dual. That's essentially, and that's like this result, that was just for H-minor free graph. We had all the results all for H-minor free graph. Just getting it for H-minor free graph, that was the stuck paper, and it's very complicated. Like this is non-trivial, exactly. Go from bounded genus graph to general graph. But say, what will happen essentially for this one? Do we have any other pen or not? I will consider essentially these things. OK, so it is not that. So let me just do this one. I will consider the dual of this graph. So I want to say this one now for the, if there is no pen. Now I wanted to consider the same problem. Now I will consider the dual of this graph. So that's a dual essentially that you will consider it for this graph. And in the dual, you delete these edges. The same edges that you have deleted in the deletion version, you are doing it for the contraction version. And now let's see what will happen when you contract it. So then you will continue. Now let's see, I want to, essentially, I will delete these edges. But instead of delete, essentially, when you delete, and the one important thing actually is that when you, this is important, the treewidths of a graph and its dual are equal. So that's the important thing. The treewidths of a graph and its dual are equal. So here, let's see, I mean, when I delete here, what will happen in the primal? That's actually very good things that you will see how will happen. So let me, I mean, essentially, so what does it mean? It means that like here, for example, I want to delete all these edges. Here I want to delete all these edges in the dual. Good. Let's see what will happen if I, when you delete this thing, it means that in the primal you will contract them. So what will be the shape? So these edges I will contract essentially. This one, this one, this one, this one, this one, this one. So that the shape that would be here. So I have the layer 0, I have it here. Then the layer 2, I don't have it essentially. So everything will essentially be collapsed into one vertex. Then here, I mean, those edges, you will keep it. So the 0 guy, again, you will keep it here. So then these edges, again, have such a things. Then you will continue again for 1 guys. And then again, for this last guy, essentially, you contract everything. So that's the thing that essentially happens for these things. When these layers, you will delete it there, it means you are contracting here. And why it has bounded treewidths? Because when you delete there, then it should have the same treewidths of these contracted things. So these contracted things essentially should have the same treewidths. And that there, because of that deletion version, we knew that it has bounded treewidths. So here it should have bounded treewidths as well. And I mean, if you want to see also, you can see directly also here, because this is essentially called one sum of a set of graphs that each of them has bounded treewidths, so it should have the things. Here, I mean, that was for the grid. You should be a bit more careful. So this was essentially the idea for the planar graph. That was the whole idea that you can get it from this. Now I want to say, I mean, for bounded genus graph, like for planar graph, one thing also can happen. Should I draw maybe something here? For example, I mentioned that you can consider the grid, but in a sense, I mean, you should consider some special cases also for this planar graph. Let me just draw something here for planar graph. The issue that you may have it is something like this may happen. Okay, maybe actually here I could say, yeah. So actually, I mean, the planar graph case, it might be the case that inside one of these things, this is still planar actually. Sometimes you need to consider. Inside this, you may have another large grid also here. This is still a planar graph. Maybe also here.
This is disconnected from these?
No, these are not disconnected. It might be connected actually. So it might be connected. Now, let's see what will happen. So here, if we contract this guy, so it might be the case that we contract these guys. So when we contract this guy, something like this will happen. When you do the same thing, so you will get this graph essentially. Then you will get this contracted graph. That would be corresponding to contracting all these parts essentially. Say I will contract all these parts. Then that would be corresponding to this vertex. And then the continuation of the graph would be like this. However, there is a catch here. What will happen to these guys? These guys, they may come again here. They will form another. So from this guy, in a sense, you also get another. So the whole boundary of this would be, like the whole boundary of this will be contracted here. And then from that, you start again with a big clique. And for this guy, again, this is corresponding to this guy. This is corresponding to this guy. Also, you get another clique here. Note that this cannot happen. If this is a large and this is large, the treewidth of this is large. Again, another thing that you need to know, the n time, like k by k grid, so I'm writing it here. So k by k grid has treewidth k, or order k. So this has a large, can you see this one? So this has a large treewidth because it is a large grid. This is also another one, which is a large grid that exists. However, there is a catch here. So if this happens, this does not have a bounded treewidth. However, this does not happen because when you do this BFS, you will go through them, and also here you will contract some of them. You will contract here, and also here you will contract it. So what will happen for the planar graph when you do these things? So you will the whole thing become like a tree essentially. You start from these things, but everything becomes like a tree. You will come from here, then you have here some things, and then you will here. From this case, you get 3 vertices that are going, and now for each of them, you will continue the things.
So you're not recursing. You're just saying the one shot it will go.
Yeah, one shot will be like that. I don't recurse. But I will say in one shot something like this happens. And the whole thing here, essentially the whole thing that happens was just a path. But I want to say in general case will be not a path, would be a tree. Still that theorem that I mentioned, it is correct. You can just use that theorem. But if you want to also use directly, if you don't want to use that duality theorem, if you want to use it directly, again, you can see that the whole graph is a one sum. So the whole tree is a one sum, and the treewidth of each piece is bounded. If you know that if you have one sum means essentially 3 of these things together, still the treewidth would be the maximum treewidth that you have. So the treewidth would be bounded. Okay, so this was for planar graphs. However, I want to say, so now let's go for bounded genus graph. So for bounded genus graph, we prove this bound. I want to give the idea of what will happen for bounded genus graph. So the good thing that can happen in this case is that when we are coming here, when we contract it, then everyone would be a separate branch. And that would be a tree. The issue is that this is not correct for bounded genus graphs. Because of the handles, what is a bounded genus graph? You have some surface, and then, they may come together. The issue is that this guy and this guy, you might have a handle here, and they will come together. And then this theorem, you cannot say this is a tree and you can do that. However, still you can say that because of the handles, the number of times that this will happen would be essentially proportional to the number of handles. So if this happens, then it is again not bad. You can say that if you have a handle, you can just, this vertex, you can just, maybe you can put it 2 separate vertex here, and then maybe put one vertex here. And essentially say that if this is a constant number of vertices that you somehow split it, still the treewidths go up by at most g, the number of handles. So that's the idea, the rough, the things, first, it was the first proof that we had it, actually, that was a combinatorial paper. That was a bit more complicated things that you had it here. But to generalize it for, that was, essentially, so that this is like the thing that you need to know something about that graph theory and topology, essentially. That if essentially there's some concept of phase width, if the phase width is small, you can decompose the graph, but if it is large, then you will get it. So if it is small, then you can split it. If not, it means that there should be some kind of cylinder, and from this cylinder, you will cut it. That was the first proof that we had. That was a bit more complicated. But the one that we had it, actually, we could generalize it also, these things, for the general graph, is the one that I mentioned here, essentially. That this thing that will happen, and you can just split these guys, essentially. And when you split these guys, you disconnect it, and then you can get essentially 3 plus g extra edges, and the treewidth will go by at most g, plus g, essentially. The bound here is better, actually. Now, for H minor free graphs, then we don't have any duality or anything. But anyway, I wanted to say something also more general. You can prove it here. So I want to say that actually this is the one that you needed for H minor free graphs. So I will just mention the main idea, and then we are essentially done here. So I will say that you can even do it with more general than that theorem that here I mentioned it. So here I need something even more general for planar graphs to prove for H minor free graphs. In a sense, I need to strengthening the induction hypothesis such that I can come up. What do I say here? This theorem is non-trivial theorem. That it took us 1 or 2 years to prove this thing. I will say don't start here. So here, in a sense, in both of these cases, you could do these things with one vertex. Essentially, we have done some BFS from one vertex. Here, I want to say that this theorem is correct. If somebody somehow pre-colored for you not a vertex, a set of edges already in the graph is pre-colored. Good? So some of the edges, somebody came and did, so this is a bit, that's essentially that started from that paper that I mentioned for bounded genus graph. So this is more general. You consider a planar graph. Some edges, somebody has pre-colored for you, like with the color 1 or something. What's the meaning of that? It means that, for example, you cannot put, so these k colors that you have it, somebody came and said these edges should be in the color k. You cannot change that. Then the question is that, can you still extend the rest of the things such that you can get the result or not? That's essentially, again, some interesting. So that's the thing that we prove it essentially here. It says that as long as we have a start with a tight pre-colored edges. What's the meaning of tight? Means 2 things you need to have it. First, the number of connected components say should be bounded. Again, I think this might be generalizable more than that, but even generalizing this part is not easy. And the other thing is that treewidths of radius R neighborhoods is f of R. So for any R neighborhoods of this guy that you will consider, say there is only one connected component. For any R neighborhood, if you have this guarantee that you can get it f of R, then it should be bounded. So this is called a tight pre-colored. So I want to just quickly mention that why. So still this theorem is correct for this case. Now let me just say the hard things for the H minor free graph and then finish it. We can. Okay, so for H minor free graph, that's essentially the main theorem that we are using. That's essentially graph minor, I think 16, that they prove this theorem. That any essentially H minor free graphs can be written in a sense as a Clique sum of some graph that each of them is almost bounded genus graph. So we proved almost for bounded genus graph. Now essentially that Clique sum. The Clique sum is the part that kills you essentially. And almost embeddable means essentially bounded genus graphs, maybe except a few apices that are going, again, these are constant number of them, and a few vertices. Vertices mean non-planarity, but this non-planarity, they have bounded path widths. So still, I mean, you can do good things for them. So these are not the main thing. The only thing that kills us for this result, so the previous result as I mentioned, for bounded genus graph, we had it in soda. It took us, I mean, several years, and we knew that was the thing, is this Clique sum. So the Clique sum, what is the meaning of clique sum? Clique sum of these two graphs means that you have two complete graphs. You say that I will say G is a clique sum of these two. If you put these complete graphs, you put them together, and there's some order you will do that, and then you identify these things. So far, everything is good, but you may delete some edges. So this deletion is the one that we didn't have the difficulty for that deletion version of the problem, because you delete these edges, and if they are not there, then it is fine. However, this is essentially that's the thing. When we prove it, when we want to prove this theorem for general case, when you want to delete some of these things, at some point, I mean, like in the previous graph, that was essentially the thing. So in the previous graphs here, you may color this edge and you may color this edge. But when you want to put them together, but when you color, it means that you want to contract them. But when you put them together, then this edge just disappears. So, and you needed to contract this edge because that was maybe a very long path. You want to contract this edge such that it becomes one vertex and has a bounded treewidth. But you don't have this edge anymore. And this is the one that essentially kills all the argument. So because of that, essentially you need to do lots of complicated stuff to essentially, that's the way that we obtain it. So this is just the general idea and then we are done. So when this is like the clique sum, you can consider it again as a tree. So this is a big graph. This is the first apex binary field graph. Then from that, there are the children of these things. Again, there are bounded treewidth graphs. And no, almost embeddable graph. From, again, there are some children of that and so on and so forth. However, the catch is that from this big guy, when you want to do that, this big guy, when you color the edges, you may have some edges colored. This edge, when it comes to clique sum with this child of that, this has some pre-colored things because you somehow colored it in the parent. You want to keep the color of this guy. That's the thing that tight things is important, that somebody forced you that you should color this edge with these things. And then again, this thing forces something on the children of that. And it is important, that will mean not summed up, because if summed up, then everything in the thing would be a mess. Everything will be pre-colored. You don't have any flexibility. But you can show that essentially only 3 edges will go in the next level that are pre-colored. And these 3 edges would be corresponding to paths, essentially, to something that we will show. So essentially, for each of them, we will realize some path that for each of these clique sum that it is deleted. So if it is there, we are fine. If that edge is deleted here, it's not really exists in the graph. In the child guy, I will find the path corresponding to that such that I can contract it and get that structure that I want. And that's essentially the whole idea of that. You need to do these things and you will find the shortest path, and it is called test structure. And this is the nice theorem that, I've just mentioned this nice theorem and that's it, I think. So this is actually a nice thing that say that treewidth of radius, this is a very important thing actually. I think it might have some other application. Treewidth of radius R neighborhood of order 1 shortest path is f of r. So if you have f of r things in the, like in say in planar graphs or even even the planar graph, the treewidth of shortest path, R neighborhood of that is bounded by f of r. And the danger is this one. So essentially, I want to say this cannot happen because you might have one path. So if it is not the shortest path, what will happen? You may come, this guy is coming here. This is just some path between this guy. So you cannot say this one for arbitrary path is correct. Because if you consider this, consider the 2 neighborhood of this guy. Like any vertex which is at the distance 2 of this guy. Then it would be the whole grid. So it is not a small. The only thing is that if it is a shortest path between 2 vertex, then you can do these things. And why? Because you cannot have such a things anymore. Because if that was the shortest path, you could just use this edge. And that's essentially the whole idea for this will be used on that pre-colored stuff essentially that we use shortest path. And that's it. So we are done with that. These are the main open questions essentially. So the main open question is that we could prove this one for out H-binary free graph for deletion and for H-binary free graph for contraction. What else we can do that? Can we do it for other graphs? I mean, I think this is not the, I don't see by any means these are the boundary. I think you might get it for random graphs or other type of graph, you get this theorem. And this theorem are very useful because lots of the time the people try to prove something, but when they try to prove it, then it would be dirty because this would be in the proof, this decomposition. I want to bring it outside of the proof. Say, prove this one, then you apply these applications for that. That's essentially the thing that we have done it so far. Bring the main structural theorem out of that and say, okay, the rest is the one that you know. And this is the main thing. Can we do it for more things? And of course, for a spanner thing that I mentioned, for a spanner still we need something to apply this thing for lots of other contraction things. That's it.
Question?
One of the I wanted to ask is, for any given graph, can you find the smallest minor, smallest graph, which is such that it's a minor free graph for that graph?
Yeah, I think, we say, I'm not so sure it is currently practical, but you can just essentially, yeah, you can do that because for any graph, there is an algorithm for that essentially. So you just try all graphs, small graphs, and say you can only consider the cliques essentially. And for each clique, you will say, can you find the disjoint path for this vertex and this problem can be solved in polynomial. This is one of the most non-trivial things in this graph minor. So if I give a set of pairs, can I find disjoint path from Si to S1 to T1, S2 to T2, S3 to T3? If you can solve that problem, then the problem that you mentioned would be essentially, that comes essentially as a somehow generalizations of these things. So you will guess these things. It still is not completely trivial, but that's essentially the idea that, so you can do it.
So
but
I guess for graph of order of like n nodes,
yeah,
it's definitely kn plus 1 minor free, right?
Yeah.
But is there
okay, so one other thing actually I mentioned. So all these algorithms that I mentioned, that's the beauty of this thing. You really don't need to know the minor free. You just apply this algorithm that I mentioned. What was the algorithm? Essentially, you will just do BFS from one vertex.
Right.
So that was essentially the whole of them were this practical algorithm. This is the one that if you want to implement algorithm, this is the one that you should implement. Consider one vertex, do the BFS. Right. And then every layer I, you will delete it.
Right.
Most probably for lots of, I will say, practical problems, when you contract this one or delete these things, it should have a bounded treewidth.
Right.
So
but the constant for that the algorithm would depend on the h.
Yeah, but I'm not so sure. That would be a bad algorithm. These are all worst case. Right. But if you want in the practical case, it might be very. You can get a. What was that?
Theoretically, can we find a constant, a small graph?
Theoretically, theoretically, you need to do that thing, and I'm not so sure the running time is good if you want to get it. But the issue is that, this is the whole idea is just analyzing this algorithm, very simple algorithm for this graph decomposition. You consider one vertex, do the BFS, and cut the layers I mod K. And most probably, I will say lots of these graphs, maybe all of them have a small treewidth, then you will solve it. Maybe a few, they don't have a small treewidth. Then you do approximation algorithm maybe on them. And I will say these are not very bad, essentially. Or do any other technique on that. That's the heuristic that, all this work that gives that heuristic, essentially, for you. So you don't need to know any about H minor free graph. These are just some analyzing that for this algorithm is good heuristic, essentially, in practice. Good? Okay. I'm sorry that I finished 20 minutes sooner. But I should have started 3.